what we proved is that Laplace of f convolution g equals to product of Laplace of f and Laplace of g. Now, if I take Laplace inverse of both sides, I'm going to get Laplace inverse of Laplace of f convolution g equals to Laplace inverse of Laplace of f times Laplace of g. So we're going to get f convolution g equals to Laplace inverse of Laplace of f times Laplace of g. And now if I will use capital F for Laplace of little f and capital G for Laplace of little g, then we're going to have f convolution g equals to Laplace inverse of f times g. F and g are capitals. So in general, if we start with two functions, capital F and g, and if we want to find Laplace inverse of them, so to do that, we'll do two steps. First one, we'll find f and g, which are going to be Laplace inverse of capital F and Laplace inverse of capital G. And the second, we find f convolution g, and as soon as we know f convolution g, we know what Laplace inverse of f capital N times capital G is going to be, convolution of f and g. That's the step that you're going to be doing if we need to find Laplace inverse of product of two functions. We're going to be using convolutions. Next example, we want to find Laplace inverse of 1 over s squared plus k squared squared. So 1 over s squared plus k squared squared equals to 1 over s squared plus k squared times 1 over s squared plus k squared. That implies that in our case, capital F and capital G, so capital F of s equals to capital G of s equals to 1 over s squared plus k squared. Little f and little g are going to be Laplace inverse of f and s correspondingly. So we're going to be Laplace inverse of 1 over s squared plus k squared. So that is going to be 1 over k sine of kt. Now, to find Laplace inverse of f times g, that is f convolution g. So we're going to get integral 0 to t sine of kv times sine of k times t minus v, and 1 over k, I will pull 1 over k times 1 over k squared, 1 over k squared in front, and integral with respect to e. I will use the property that sine of a times sine of b equals to 1/2 cosine of a minus b minus cosine of a plus b. So if we use that property, we're going to get 1 over 2k squared integral 0 to t cosine of difference. So we're going to get cosine of kv minus k of t minus v. So we gain k times 2v minus t minus cosine of sum, cosine of kt dv. So it equals to 1 over 2k squared. Antiderivative with respect to v is going to be 1 over 2k sine k times 2v minus t. With respect to v, the cosine of kt is a constant, so v times cosine of k t, and we're doing it v equals to 0, v equals to t. So substituting upper bound, substituting the lower bound, we're going to get 2k cubed on the bottom and sine of kt minus kt cosine of kt. And that is going to be Laplace inverse of 1 over s squared plus k squared. If we have a following problem, initial value problem, so we have second derivative of y minus y equals to function on t, function g, where y prime of 0 equals to 1 and y of 0 equals to 1. Okay, so we want to solve that initial value problem. We're going to use Laplace transform, so we take Laplace of the left side, we take Laplace of the right side. Laplace of second derivative is going to be equal to s squared Laplace of y minus s minus y, 1, because y prime of 0 equals to 1, and y of 0 equals to 1, s times 1, minus Laplace of y equals, I will start using just L of g for the right side. So Laplace of y is going to have coefficient s squared minus 1 equals add s at 1 to both sides, divide by coefficient of Laplace of y, reduce the first one into 1 over s minus 1, Laplace of g over s squared minus 1. So we have y equals to Laplace inverse. We take the Laplace inverse of both sides. Laplace of the first term is straightforward. It's going to be e to the t plus Laplace inverse of Laplace of g over s squared minus 1. So now we concentrate our attention on finding Laplace inverse of that expression. So if we look at that expression which we have here, so we have Laplace of g over s squared minus 1, so we're going to treat that as Laplace of g times 1 over s squared minus 1. And if we want to find the Laplace inverse of that expression, that is going to be equal to, we want inside here is product, so Laplace inverse of product equals to, we want to have convolution at the end, so it will be convolution of the first one times Laplace inverse convolution of Laplace inverse of the second one. So let's find Laplace inverse of 1 over s squared minus 1. That is Laplace inverse of 1/2 1 over s minus 1 minus 1/2 1 over s plus 1, so it equals to 1/2 e to a t minus e to a negative t. So if we know that, then we substitute it here, so we're going to get Laplace inverse of g times 1 over s squared minus 1 equals to g of t convolution with 1 over e to a t minus e to a negative t. So it equals to, if I will rewrite convolution in terms of integral 0 to t 1/2 e to a t minus v minus negative t minus v g of v dv. And now I'll go back to finding what y is. So y equals e to a t plus Laplace inverse of that expression, which is this guy. So I'll take that one and substitute it here. Take it, substitute for this guy. So I'm going to get integral 0 to t 1/2 e to a t minus v minus e to a negative t minus v g of v dv. So we get our answer in the integral form.